of the B+3 index structure. I will introduce the hash index structure and then we'll discuss that in the next class. The hash index structure, as we talked about earlier, reduces your search cost to almost constant time. So it's O1, and it's really good for equality search. There are three variants: static, extendable, linear hashing that is discussed in the textbook. We will not discuss linear hashing. We will only cover static hashing and extendable hashing. Hashing. So static hash, you have your search key coming in, you apply a hash function, and that could be an arithmetic function of this form. Say k is an integer, then you get one of these primary bucket pages. If not enough slots are available there, you go to the overflow pages. Because n is a fixed parameter in the static hash, you have to take hk mod n, and if multiple of these search keys collide onto the same bucket, you have to fit them onto the overflow pages for the corresponding hash key. Okay, so primary bucket pages are never deallocated. Even if you go ahead and delete a bunch of stuff, these pages can be empty. Just like with the B+3 index, the data entries in the primary bucket pages or the overflow pages can follow any one of those three alternatives: the alt record, alt RID, alt RID list that we talked about. Now again, the search algorithm is pretty trivial. You basically apply the hash function, go to the correct bucket, and then do a full scan of the bucket page or the overflow pages if needed. Therefore, the average search cost is O of 1 plus the number of overflow pages per bucket. Okay? If n is large enough, usually it will just be O of 1. There's not many overflow pages. As an example, how exactly does this hashing work? Let's say you have 3 bucket pages and we follow alt record, which means the data entries are going to be large. Let's say only one record fits on a page. This is what the static hash index would look like if you were to do it on the movie ID. Let's say the hash function you're given is this. A is 1, B is 0, so it's A times K plus B, which is K, mod M, which is mod 3. And so now the alt record means the data records are there on the pages of the index. You have to take 15, which is the movie ID, mod 3 is 0, and therefore 15, which is avatar, that record will be in this bucket. Similarly, 52 mod 3 is 1, and therefore that is in this bucket. 20 mod 3 is 2, it's in this bucket. 74 mod 3 is also 2. There's no space on the primary bucket page. You add a list of overflow pages and you put this record in the overflow page. So it's a pretty simple data structure, and each one of these pages can be on disk. Some of these pages can be cached in memory, but based on the hash function, you know which page to retrieve. Okay, so this is just what I walked through. What is the insert procedure? Same as the search procedure, do an equality search. If there is space in the primary bucket page, put the slot in there. If not, go to the overflow pages and then find a free space and put it in there. Delete, again you start with the equality search. If you find a record with that search key, delete that record. If an overflow page becomes empty because all the records in there have been deleted, the overflow page can be tossed out. You don't need it. Primary bucket pages, even if they become empty, are still kept around. What are the issues with the static hashing procedure? Well, n is fixed. Therefore, you can only hash to one of n buckets. That could cause a problem in both directions. If you have a lot of records, everything might end up overflowing, and therefore the number of overflow pages can grow substantially if you keep adding a lot of records. That will degrade your search cost. It will no longer be constant time. It will be O of 1 plus number of overflow pages per bucket. If you do deletes and you delete a lot of records, there are very few records left, the size of the index is still at least n primary bucket pages, and so you're wasting a lot of space on this. Whereas with the B+3 index, its size adjusts itself based on the deletes and the inserts. Now, full reorganization is needed if you want to mitigate this issue of having too many overflow pages or having a lot of free space on the primary bucket pages. You basically have to alter n. You have to make n larger or make n smaller. That means you have to redo the entire index from scratch. That could be an expensive operation that will block query processing. Therefore, you don't do it that often. The other issue with static hashing is skew. skew basically means multiple values of the search keys domain get mapped to the same bucket. That is, one bucket is disproportionately represented in the hash function, the other ones are not. Yes?
Is the page here just the physical page or just only one record?
Which one?
I mean, page, overflow page.
It's a page, just like in a B+3 page, like
Okay.
overflow pages in the B.
For the primary page, there may be lots of records can be.
Yes, multiple records can
page.
fit into one page.
Okay.
That's true for the overflow pages too.
Okay.
It's a regular page that we've been talking about.
Okay.
Okay? So now the hash function, the skew in hashing means when you take a random sample of values from the search keys domain, it doesn't get uniformly distributed across the buckets. Skew basically means there's a skew in the distribution of the hash key values. Some buckets might end up getting disproportionately too many keys mapped to them, whereas others do not. Okay, so then that is called a bad hash function because it doesn't spread the values uniformly across the buckets. For our purposes, we don't have to worry about this sort of skew because this is a mathematical issue that's well studied and it's pretty much solved. People have devised hash functions for every attribute domain, integers, floating points, strings, that have near uniform distributions. But what we do need to worry about is duplicates. If your data entries have duplicates, if you have multiple movie records having the same year, suppose there was one year where there's like enormous numbers of movies came out, that is unavoidable by the hash function because all of them will get mapped to the same bucket regardless of what hash function you use. That means you could have multiple overflow pages for that bucket alone. This issue is difficult to resolve here, okay? Because all of these data entries have exactly the same search key value, and therefore they will get mapped to the same bucket, regardless of what hash function you use. This is where, not exactly here, there's a second hash index that we'll talk about next. It's called the extendable hash or the dynamic hash that mitigates these issues regarding n being either too large or too small. Okay, so we need a dynamic hash index that will grow or shrink based on the actual data values that are getting indexed. So what does extendable hash look like? The idea is instead of hashing directly to the data pages, you use a directory structure. And this directory structure is allowed to grow or shrink. This directory structure contains pointers to the data pages. So here's an illustration of what the directory structure looks like and what the index looks like. Unlike a static hash, where you just apply a function h and then directly go to the page, here you have this directory of pointers that point to buckets, the pages of the data entries. Okay, so now there are a bunch of things here. Let's go through each one of them. The directory is of length, which is an exponent of 2. So it's basically in powers of 2. Here it is 2 to the 2, which is 4. So there are 4 entries in the directory. The entries are identified using the binary sequence 00, 01, 10, 11. So if you have directory with what is called the global depth, GD parameter, if that is 3, you will have 8 entries in the directory, and then they will be identified as 000, 001, all the way to 111. Okay, so this is your identification for the pointers in the directory. Now each pointer points to a bucket page. The bucket page contains the data entries, and so here it's the same kind of asterisk notation, means it's a data entry. So you have 4, 12, 32, 16, and all that. So there are, in this particular example, there are 4 slots that fit into a page. So you can have 4 data entries on each bucket page. There is a parameter for each bucket page as well, and that parameter is called the local depth. So what is this local depth and global depth? We'll get to this. But how do we know where a given data entry goes? Well, this sequence is what is going to tell you where it goes. Imagine this sequence as a very trivial hash function where you only look at the last GD bits of your data entry, of your search key values. So that's your least significant bits. So look at the last two significant, least two significant bits of your search key value. That will tell you which pointer to take. Why? What is the binary representation of 4? 1, 0, 0. What is the 2 least significant bits? 0 and 0. And therefore, 4 is in the bucket pointed to by 0 or 0. Same thing with 12. Same thing with 32. Same thing with 16. What is the least two significant bits of 1? 0, 1. So 0, 1 points to this. What about 13? Again 0, 1. So it points to this. Similarly, these other ones. Now an easy way to remember this is, instead of worrying about binary representation of the search keys, divide by 4 and take a mod. So this is just a trivial function, hash function, that takes the search key and does a mod 4. If the mod 4 is 0, you go here. That means all multiples of 4 go here. If the mod 4 is 1, you go here. All of these are basically 1 plus some multiple of 4. These are all 2 plus a multiple of 4. These are all 3 plus a multiple of 4. Okay, so that's an easy way to remember where a search key goes based on this binary representation here. It's just a trivial hash function that does a mod based on the 2 to the global depth as the parameter. So what is this local depth and what is this global depth? So let's come to that. But first, what we need to know is these bucket pages, unlike a static hash where these 4 bucket pages are all you have, in a dynamic or in this extendable hash, this directory structure can actually double or shrink by a factor of 2, and corresponding the number of bucket pages can double or shrink. So here's an example. Let's first look at what the search process is going to be. Like I said, 17 is your search key. Do a mod 4. Mod 4 means 1, so take this pointer and you know 17 is in this bucket. Okay, so equivalent saying is just look at the last GD bits of the hash function value. So here, this is the binary representation of 17. The last 2 bits are 0, 1. What about 42? Which bucket does it go to? C. Okay? The binary representation, the last 2 bits are going to be 1, 0. Therefore, you go to bucket C. It's not present in bucket C. So the search query returns an empty result. What is the I/O cost of the search process? It's constant time. Here in this case, it's exactly 1. Okay, let's assume that the directory page itself, the directory is a bunch of pointers, right? That itself is a page. Or it could be multiple pages. Those pages can be easily cached in buffer pools. Okay, so then if you assume the bucket pages are not in memory, you need 1 I/O to get the corresponding bucket page. Okay, so it's still constant time. What happens when you insert data entries? Well, again, as with the other indexes, first thing you do is search for K. If that corresponding data page has free slots, add the record there, add the record ID if you're using alter ID, and you're done. But if the data page has no more space, what do you do? And that's where this local depth and the global depth parameter come into play. If the local depth on a page parameter is strictly less than the global depth parameter, then you partition that bucket into 2 buckets, and the second bucket is called the split image. The local depth parameter for both these new pages are incremented by 1. Okay, and then you insert the record correspondingly based on what the last bits are. If the local depth parameter is equal to the global depth parameter, after creating the split image page, you increment the local depth for both, but in this particular case, the directory doubles in size, and therefore the global depth increases by 1. In this case, you have to duplicate the other pointers in the directory, and basically they will occur twice in the directory. So this means the directory grows in spurts. It doesn't grow contiguously. You keep waiting till LD equal to GD happens, and then that's when the directory doubles. When the directory doubles, the GD will increment by 1, but then every other bucket page's LD might still be less than the new GD, and therefore the directory will, it's quite likely it will not double again in the near future. So let's do an illustration of how exactly this works. So this is the state of the extendable index that is given to you, and these are the data entries present. First you need to check, is it valid? Well, it's valid. All of these mod 4 are 0, mod 4 1, mod 4 2, mod 4 3. Global depth is 2, the directory's number of entries is going to be 2 to the 2, 4. The local depth parameter for each bucket is set at 2. Okay? Let's insert 24. Which bucket should it go to? A. 24 mod 4 is 0. Right? But A has no space. What do? You apply the algorithm for the insertion. You need to check what is LD versus what is GD. And in this case, LD is equal to GD. Therefore, apart from splitting this page and incrementing its corresponding local depth, global depth also has to increase. This is what the split image of bucket A will look like, and the notation we will use for the split image is A and then A2. You could use another notation which is A1 and A2, that's fine. Doesn't matter. You can even call it bucket page E. What does it mean? How do you redistribute the keys? Now, in the B plus tree, the way the redistribution worked was in sorted order. You do a rotation. Okay? If you're borrowing from your right sibling, you take the least values in your right sibling. If you're borrowing from your left sibling, you take the highest values in your left sibling. Whereas here, the splitting of these keys that go into bucket A across these two new buckets happens by the third significant bit, third least significant bit. Okay? That is because the local directory, local depth has incremented by 1, so now you need to look at the last 3 bits instead of the last 2 bits. Looking at the last 3 bits versus the last 2 bits, the last 2 bits here are both 0, 0 and 0, 0. That is not going to change. It's only the third least significant bit that is different. 0 for bucket A, the new bucket A, and 1 for the bucket A2. What does that mean? That means this entries in this new bucket are going to be 0 mod 8. The entries here are going to be 4 mod 8. Okay? You can verify by writing out the binary representation of these numbers that the last 3 bits for these numbers are 1, 0, 0, whereas here it is 0, 0, 0. Okay, so the way to think about this is so far you have looked at mod 4, but now this bucket has split, its local depth has gone to 3, and so you can see the local depth parameter is set to 3. So now you need to look at mod 8, which is 2 to the 3. And mod 8, this is 0, and this is 4. Okay? So this is what the new index structure looks like after the insertion is done. We split bucket A and bucket A2, and because the global depth went up by 1, the directory has doubled in size, and instead of having just 2 bits, you need to have now 3 bits represented for each of these, and so you go from 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1. Okay, so 2 to the 3 is 8. So you have 8 entries in the directory, but you don't have 8 bucket pages. Even though the directory doubles, the number of data pages, number of buckets here does not double. And why is that? Well, the local depth is what determines how many bits you need to look at. And this bucket A and this bucket A2, the local depth was 3. And here, mod 80 means 0, 0, 0 will point to this one. But bucket A2, you want mod 8 is 4, which means 1, 0, 0 is the pointer that points to this one. But all these other bucket pages that were there before, B, C, and D, their local depth has not changed. It's still 2. So you only need to look at mod 4. Bucket B was what? It was 1 mod 4. 13 is 1 mod 4. 41 is 1 mod 4. 17 is 1 mod 4. But the global depth is now 3, which means you have 2 pointers that could actually point to that bucket page. 0, 0, 1 is 1 mod 4. 1, 0, 1 is also 1 mod 4. Okay, what is 0, 0, 1? It's 1. What is 1, 0, 1? It's 5. Both of these are 1 mod 4. So both of these directory entries point to the same bucket page. Okay, so now if a new search key comes in, you do the global depth 3, so 2 to the 3 is 8. Do a mod 8. If the mod 8 is 0, you go here. If the mod 8 is 1 or the mod 8 is 5, you come here. Okay, does that make sense? If the mod 8 is 2 or if the mod 8 is 6, then you go here. Okay? Yes?
Which Which parameter decides the size of the bucket?
Which parameter?
Yeah.
Oh, that's determined by the record size. The
Okay.
data alternative that you follow, alt RID, alt whatever, the data entry size. Your page size is given. You can calculate the number of slots in each page, right, based on the record length.
Yes.
So here we are saying that 4 data entries fit on a page. Okay? So that's orthogonal to which index you use. It's a page property. That's why we saw the record layouts on a page and stuff like that. Any other questions? So this is how the extendable hash index works. You have bucket pages pointed to by directory entries of pointers. If a bucket fills up, there are no more free slots. You create a split image, and then you increment the local depth by 1. But if the GD and the LD were the same, the global depth is also incremented by 1, and the directory doubles in size. But all the other bucket pages are not going to be split. Therefore, you will have multiple pointers, 2 pointers to be precise, pointing to these other bucket pages. Whereas for the split images, there'll be only 1 pointer pointing to them. Okay? Notice that only the split image ones have the new local depth of 3. The other buckets have a local depth that is less than the global depth. Okay. What happens if you insert 18 into this index structure that is given to you now? Now this is an extendable hash index that's in a valid state. Now I want to insert 18. Where does it go?
C.
Why?
18 mod 8, 2.
Mod 8 is 2. Yep. Mod 8 is 2, so you go 0, 1, 2. So this is the pointer, so it goes to bucket C. Okay? What about inserting 25? Yes. So there are 2 ways to do this, right? You can do a mod 2 to the global depth, which is mod 8. Mod 8 is 1, so the first pointer is what you want to take, not the 0th pointer. And that sends you to bucket B. The other way is to just write down 0, 0, 0 to 1, 1, 1, and then look at the last 3 bits, and then the 0, 0, 1 is the last 3 bits. That also tells you bucket B, obviously. There's not enough space in bucket B. Only 4 slots can fit. So now you have to split bucket B. But the insert algorithm tells you that the local depth is strictly less than the global depth. Therefore, the directory is not going to increase in size. All that will happen is this bucket will have a split image. You have to redistribute these keys based on mod 8 being 1 versus mod 8 being 5. Okay, so far, because the local depth was 2, you only needed to worry about mod 4. But because this bucket is getting split, its local depth increments by 1, and now you have to start doing mod 8 instead of mod 4. And so this will be the new directory structure. 1, 13, 41, 17, which one of these are 5 mod 8? Only 13 is 5 mod 8. Okay? So 13 goes away from bucket B to its split image bucket B2. All of these are 1 mod 8, and therefore they stay here. Okay, so notice that these pointers in these entries of the directory, which both of them were pointing to B, but now only this one points to B, this one points to its split image. And also notice that the local depth parameter has to be incremented by 1. This one, local depth becomes 3. This one goes up from 2 to 3. Okay, does that make sense? You can tell this structure is valid because if the local depth is equal to the global depth, only 1 pointer needs to point to that bucket page. If the local depth is less than the global depth, multiple pointers will point to that bucket page. Okay? Pretty interesting, huh? So this way, you can allow the directory structure to keep doubling in spurts, but the number of bucket pages is not wasted. You're not going to double the number of bucket pages at once. You only grow them based on the need for splitting the bucket pages. Okay, what is economist? What happens when you delete records? Just like with the B plus tree, we saw if you keep deleting, you need to make sure that there's occupancy. Whereas notice that for these hash indexes, we don't care about the occupancy. We can allow less than 50% occupancy. But if the page becomes empty, it's just sitting there, what do we do? Well, for the delete operation, you search for the record, obviously. And then if you find a record with the same search key, delete it. The problem is, If the page becomes empty, it's wasteful, what do you do with it? That's when you merge that page with its historical split image. What is the historical split image? The historical split image says which page did this page split from in the past. Okay? And that is the historical split image. It will happen when we can merge this page with another page that has the same last GD minus 1 bits in the string representation in the directory. Once you merge them, both of their LD will shrink by 1. And therefore, you have to go and update the directory pointers accordingly. Now, if all split images get merged back and all the bucket pages end up having LD that is exactly 1 less than the GD, then the entire directory can be shrunk by half. And only at that point does the GD get decremented by 1. Okay, so again, the pages can get merged in many ways, but the directory will remain the same. Only when every page in the bucket pages have LD less than 1 will the directory shrink. So the directory shrinks in spurts. Okay? Throughout all this, the LD can never become greater than GD. It can only be less than or equal to the GD. So how does this work? Let's look at the illustration. This is the state of the index that is given to you. Make sure it's valid. Mod 4 is 0, mod 4 is 1, mod 4 is 2, mod 4 is 3. So everything is correct. Local depths are all 2, global depth is 2, everything is fine. Delete 41. What is mod 41 mod 4? 1.
1.
Go to bucket B. 41 is right here. Delete it. That's it. Nothing else. You just delete it. Next, delete 26. 26 mod 4 is 2. Take this pointer. Come here. You find it there. Delete it. And now you realize bucket C is empty. What do? You look at the historical split image of C. To do that, you need to look at the last GD minus 1 bits. GD minus 1 is 1. And the last bits means 0, 1, 0, 1. A has 0 as the last bit. C has 0 as the last bit. So A and C are the historical split images. Therefore, you want to merge C with A and decrement its local depth. Okay? Once you have merged them and you've decremented its local depth, because the local depth is less than the global depth, multiple pointers from the directory will point to the same bucket. Okay, so the bucket pages have shrunk, the directory is still the same size. But because the local depth is less than the global depth, this page, bucket page, has 2 pointers coming from the directory. Okay? What does this mean? Local depth is 1, therefore you need to take mod 2 to the 1. Anything that is 0 mod 2 goes here. These two have 1 mod 2. To distinguish between the 1 mod 2, you have to look at mod 4. This one is 1 mod 4, this one is 3 mod 4. Okay, so this is the state of the directory after the delete has been done and the merge has taken place. Any questions? Very interesting algorithm, right? You basically manipulate these parameters, local depth and local depth, to keep track of what is the number of pointers you get, what is the calculation you need to do to get the records there. Okay, so why did we pick A to merge with? Why not B? Why was C merged with A instead of B?
Because they have the same like the
Least significant bit. Yep. Both A and C, you need to look at the last GD minus 1 bits. They need to match. The only one that matches the last GD minus 1 bits is A. Okay? That is how you can preserve the mod 2 to the K property. If you merge B and C, this is 1 and this is 2. It's not mod anything. You can't do mod 4 and then have mod 4 1 and mod 4 2 in the same page. Whereas here, because the last significant bit is the same, you can do a mod 2, and if mod 2 is 0, both pointers go to here. Okay? That's why you have to figure out which is the correct historical split image. Now again, bucket merges and deletes are quite rare, just like I said for B plus trees. So directory shrinking is actually very uncommon for the extendable hash. Okay, let's compare static versus extendable hash. Why not let n in the static hash index grow and shrink? Yes, you have to keep rehashing it. You might have to move records across pages. There will be a lot of random IOs. Okay, so extending n in the static hash is painful. On the other hand, the directory structure for the extendable hash index is typically much smaller than the data pages. Let's say you're able to pack 20 data entries into a page. So the directory structure is 20 times smaller than the number of data entries. Okay? And that typically can be cached in the buffer pool, whereas the data pages can be, the bucket pages can be on disk. Now with static hash, if I change n, even if I increment it by 1 or decrement it by 1, the entire organization will change, because hk mod n and hk mod n plus 1, there's no direct relationship. You can't just say I'm going to just move to my neighbor. You might go all the way to the end now, depending on what the value is.
Well, if n is the power of 2 and then we increment it by 2, I mean twice the size, you will get the same effect as the dynamic hash one.
Not really, because even if you have n doubling, you have to pick which one is mod 2 to the 1, 2 to the k or something.
Yeah.
And so every page you'll have to rewrite to a new page. Whereas with the extendable hash index, only one bucket page splits. Does that make sense? So it's the equivalent of every bucket page in the extendable hash splitting at the same time. So it's still very expensive. Okay? Now, this notion of skew that I talked about, where the search keys, the hash function is not uniformly setting it to your bucket pages, can happen in both cases. And especially if you have duplicates, overflow pages are unavoidable. If your search key is such like year, you're indexing on year in movies, it's quite likely multiple data entries will share the same search key. There is no hash function that will split them apart. So all of them will hash to the same bucket page. And because they have the same bit sequence for your local depth, they're basically going to have to go to an overflow page pointed to by the bucket page. So overflow pages are unavoidable in cases of duplications in the search key values.
So for the second bullet point,
Mhm.
does it mean for like when hashing skew, you might have overflow page in both cases, but only the first one will be affected in terms of the complexity for lookup?
Yes, so this skew here basically means even if you don't have duplicates, hash function has a skew, the static hash will suffer because of that, because you have a lot of overflow pages. The extendable hash, on the other hand, if there are no duplicates but there is skew in the hash function, it will not suffer substantially. It will just have a larger directory, but you will still have an order 1 lookup to get to the bucket. Okay, that's a good point. Okay, any other questions about the pros and cons with the static versus extendable hash? Okay, so that wraps up this topic.